Okay. Now it's my honor and privilege to present Ulrich Meyer, who will give us a talk entitled Infinitesimal Actions.
Thank you all for still being here. So this talk called Infinitesimal Action, it's really a talk about velocity. So velocity at heart, the way it's usually defined, is a kinematic quantity. So as you might know, theories of motion are commonly divided into kinematics, which aims to describe motion, and dynamics, which aims to explain why objects move the way they do. For example, Kepler's law is a kinematic law in that it just describes the motion of the planet. Newton's theory of gravitation is a dynamic law in that it aims to explain why motions move the way they do. So kinematics, humble aim of describing motion, and the fundamental kinematic quantity is an object's trajectory, which is a map from temporal coordinates to spatial coordinates. That maps to each time at which the object exists. It's the coordinates of the location at that time. Now, in terms of the trajectory, we can define what physicists call the velocity of an object, or the instantaneous velocity of an object. Velocity at a time t0 is the limit of the object's average velocity over shorter and shorter time intervals. Now, so here's the limit of h as h goes to 0, and here we have the average velocity between t0 and h can be both positive and negative. Now, the definition attributes the velocity to a single time of the light. But most people think that it's a mistake to think of velocities as generally instantaneous quantities. Because what we have on the right, thinking about an average velocity is clearly a feature of a temporally extended process. It depends on the location of the object at two different times, explicitly, and implicitly on what the object does in between. And here, since a velocity is the limit of average velocities, and since the limit at a point depends on where the object is at neighboring points, most people think that also velocity at a time t0 is a feature of a temporally extended process. I want to call that the process view of velocity. Now, this kind of view you can find in that it's a view that most people have about velocity, and you can trace it back to the pre-Socratics. It's a view that it makes no sense to speak of a state of motion at an instant. Yeah, so Russell famously has this view, and a lot of people attribute the view to Russell, calling it the at theory of motion. Now, my aim in this talk is to try to persuade you that good reasons for abandoning the process of velocity. I should say from the outset that I'm not going to have a knockdown argument against the process view. If you really want to have this view, you can keep it, but I think the theoretical costs of the view are much higher than is usually admitted, and the alternative that I want to try to sell you, the infinitesimal action view, is in much better shape than people seem to think. Now, the main objection against the process view, and really the only reason why anybody needs to write a philosophy paper about velocity, is that the process view is at variance with the dynamics of velocity. So again, the dynamics is that part of theories of motion aims to explain why objects move the way they do, why they have the trajectories that they do have. And typically, dynamical theories do that in terms of the forces that act on objects. And if you look at some of our best theories, the role that velocity plays in these theories, the causal role it plays in these theories, is that of an instantaneous quantity. Let me give you 3 examples. First is, suppose we have a meteor that crashes into the surface of a planet. Then the force of impact of the meteor depends on its velocity at the time of impact. The velocity determines the kinetic energy of the meteor, and that is that kinetic energy that needs to be converted into heat in order for the meteor to come to a halt. So it's velocity at time of impact. And clearly the meteor doesn't remember where it was previously. so as to hit the surface of the planet with the right sort of force to be in accordance with laws of motion, it really isn't. It's a velocity at the time of impact. In relativistic theories, we can get something even better. Think about relativistic mass of an object. An object's relativistic mass increases as its velocity increases. It has a rest mass, but then as the faster it gets, the larger its relativistic mass gets. And it's that relativistic mass that determines how strongly an object couples to a gravitational field. So an object's velocity determines what force it feels in a gravitational field. An even better example comes from electrodynamics, which is really our first relativistic theory. Imagine we have a particle, a charged particle in a magnetic field. So here's a diagram. We have a homogeneous magnetic field that points upwards. And then here we have a charge that moves with a velocity v. Now the surprising discovery is that the force that acts on the charge is proportional to the velocity. So here Q is the charge, M is the mass, C is the speed of light, and here we have the vector product of the velocity and the magnetic field. So the force that the object feels is vertical both to the direction of motion and the lines of the field. So here it's going to kind of stick out of the board. So as a result of that, if you have a charged particle that you shoot through a magnetic field, it ends up moving in a spiral trajectory. You want to see like pictures of particles in cloud chambers that move with these spirals. That's what you get when you have a charge in a magnetic field. So here, what we have, and this, I should say, this is an amazing discovery. An object's velocity determines how strongly it couples to a magnetic field. That's amazing discovery. It's like one of the grandfathers of the theory of relativity is this problem here. Einstein was worried about this in 1905. So here, if we look at our scientific theories, we take them at face value, velocity, surprisingly, in these theories, plays the role of a genuinely instantaneous quantity. It determines how strongly objects couple to magnetic and gravitational fields. And I want to argue that process view as troubles accommodating them. Now, the idea here, so here we have the definition. And the idea of the process view is that attributions of velocity are really high-level descriptions of locations over time. So the idea will be like, the velocity in our theories plays this role, but somewhat has to be played by the successive locations of the object, because that's all that's real according to process view. And it's not at all clear how to do that. Think about an account of causation, things of causes as difference makers. And we look at this definition here, if you take any time other than t0, then since velocity is defined as a limit, it turns out the object's location at any individual time other than t0 makes no difference to the limit. At any individual time, the object can be wherever you want without influencing the limit. So location at any other time makes no difference to the velocity, so it can also make no difference to its causal effects. So it looks like locations don't play any part of the causal role of velocity. You might think, okay, this is just too quick. You might think, well, look, what the process theories ought to say is that it's not the individual location that has the causal effect of velocity, but collectively. So this is an instance of a collective causation. Now, the problem with that is that the way collective causation gets modeled in physical theories is typically in terms of vector addition. So imagine you have one mass here and all of you masses are around. Then the force that all of you exert on the mass here is a vector sum of all the individual forces that we get from the gravitational interactions. So that's how collective causation gets modeled in physics. There is such a thing, but it's addition of vectors, and in that case, every one of you is a difference maker to the force that is felt here, to the collective action of all of you. But we just saw that in the case of velocity, there's no such thing. Okay, one more attempt, and then I'm gonna let go. You might think, well, it's not regular collective action, is redundant collective causation. Imagine, we have 12 men carrying a piano upstairs, where 6 would have sufficed. That none of the guys is a difference maker to the piano getting upstairs, because if any one of them had not shown up, the piano still would have gotten upstairs. Right? So there's such a thing. That's true, they're not difference makers, but we don't want to say that none of them brought them up, that no men brought up the piano. But what we have here is that, none of them individually is a difference maker, but it's true for each of them that they're a necessary part of the sufficient cause. And each of them, you can include them in a group of 6 that's sufficient to bring the piano upstairs, and if everybody outside that group, including this one guy, had not shown up, the piano wouldn't be brought upstairs. Right? So there's such a thing as redundant collective causation. So in this case, so being part of being a necessary part of a minimally sufficient group of causes might be sufficient to be a cause of bringing the piano upstairs. That explains why each of the 12 guys is part of the cause, and also explains why a 13th guy who just comes and smokes a cigarette on the side doesn't count as a cause. Yeah, so that's great, but again, in the case of velocity, we don't have that. None of the locations other than the one at t0 is a necessary part of a minimally sufficient group of locations that we need here. Let me kind of, rather than what is a grand conclusion, here's the problem. The problem for the process here. That is, here we have the definition, and the guy on the left plays a causal role. It's utterly unclear how to use this kinematic definition of velocity to parcel out the causal role of velocity amongst the locations. And until you have some clever account, and nobody presented that, it's utterly mysterious how locations could play the causal role of velocity. Now, that's a problem for the process view. Now, you might think that the real issue here is that we haven't been radical enough the process theory. We need a process theory not just of velocity, we need a process theory of everything. So think about acceleration. Acceleration is to velocity what velocity is to location. Velocity measures the rate at which an object's location changes. Acceleration measures the rate at which an object's velocity changes. So whatever we set in favor of the process view of velocity applies equally well to acceleration. Also, acceleration seems to be a feature of a temporally extended process. Yeah, because it's about velocities at other times. So let's suppose we also accept a process theory of acceleration. Well, it's not clear we can stop there. Think about Newton's second law of nature. It relates the acceleration of an object to the external force that the object experiences. So if accelerations are features of temporally extended processes, well, then perhaps also forces need to be features of temporally extended processes. Similarly, if a force is generated by a force field, such as the one that we had here, the charge in a magnetic field, or a mass in a gravitational field, then if this is a feature of a temporally extended process, well, then perhaps also field values need to be features of temporally extended processes. So really what we need is a process theory of everything. Everything is a feature of a temporally extended process. Velocities, accelerations, forces, field strengths, and so on. That's what we need. What that requires is for you to kind of rewrite our scientific theories as a theory of these extended processes. There's a way of it's a scientific reform project, And if you're interested in how that might be done, Russell proposes something like that in the Principles of Mathematics. So if you really want to have this view, you want to have something to say about what happens in our scientific theories, that's, I think, for the process view, that's the best way forward. And Russell also famously thought that we ought to banish the notion of cause from a philosophy, so kind of explaining how the causal role of velocities gets played by locations, for him is a non-problem. Right? So yes, he thinks, well, we just need to redo all of this. If you really want to have the process view, this is the way of having it. Okay. But it's also a scientific reform project. Yeah, to paraphrase David Lewis's famous remark about mathematical nominalism, how would you like the job of having to go to the physics department to tell them that, that they need to mend the error of their ways and rewrite all the theories now that philosophy has discovered that nothing acts instantaneously? That's it. Well, if you really want to, it strikes me as unattractive. Now, what are the alternatives? Here's one alternative, not the one that I want to propose. It's the two quantities view. So what we have, like, what's the problem? The problem is that there appears to be a tension between the kinematic definition of velocity as a limit of average velocities, which strongly suggests that velocity is a feature with importance in the process, and the dynamics of velocity, where in some of our best scientific theories, velocity plays the role of a genuinely instantaneous quantity. Well, one solution, the two quantities view, is that there are about two different quantities. Now, there's a kinematic quantity and the dynamic quantity, and they're different quantities. Thule has that view. So basically, the idea here is that here's what we need to do. We postulate, in addition to the kinematically defined V, we postulate a new quantity, the W's, and new laws of nature, hitherto unknown to scientists, such that this equation here is nominally necessary. We have these new quantities, and we have laws of nature, the new laws of nature, that guarantee that these new quantities align with the, in our world, where these laws are, that they align with the trajectories in the right sort of way. The definitions, that's a nomic necessity. So these are the W's, and then what we need to do, we need to rewrite physics in terms of the W. Well, the physicists said V, will put in the W. That's the view here, and kind of, people have this view that it's a principle possible for the W's, the dynamic quantities, to part company with the trajectories. It's only in our world that the W's align with the trajectories in the right sort of way. Those are tangents to the trajectories. Luckily, we live in this world, they say, but in other worlds, it's different. So Thule has that, Carol, Bigelow, Pargetta, a bunch of people. It's another scientific reform project, and it's metaphysically extravagant. It discovers new quantities, the W's, and new laws of nature to attach the W's to the trajectories. Also, this one, if you really want to have it, you can have it, but it's metaphysically costly. I want to propose a different view, what I call the infinitesimal action. The basic idea is to take the definition of velocity and read it the other way around. Read it backwards. What the process view wants to say is that process view reads it forward, thinks that the neighboring locations determine the velocity at a time. And velocity at a time is really about these neighboring locations. Therefore, you get from the neighboring locations to the velocity. Reading backwards and say, look, we have velocity at a time, and it's a velocity at a time that it poses a logically necessary constraint on infinitesimally neighboring times. That's the view I want to solve. And we'll read the definition the other way. The main argument is going to be this is going to allow us to regard velocity as generally instantaneous quantities. But I also kind of want to sweeten the pill a little bit by giving a good company argument. By telling you about the inspiration for this view. You can think of this view as a temporal counterpart to basically everybody's view about dispositions. Think about a standard example of a disposition. X is fragile if and only if a wood breaker was struck. Now we marry this to a possible worlds analysis of the counterfactual, and we get that X is fragile just in case it breaks in the closest possible world in which it's struck. Here, if you read this, the way the process theory reads the limit definition of velocity, you ought to conclude that attributions of fragility are about features in extended regions of logical space. Yeah, but nobody thinks that that's true. Fragility isn't the feature of a region of logical space. It says something about the way the thing is in the actual world. The China vase is actually fragile. That's why we make sure not to drop it. It's about the actual feature of the vase. Now with fragility, a lot of people have like a modal counterpart of the two quantities view. Think, yeah, fragility, really kind of high-level property that has a categorical base that isn't dispositional. It's a crystalline structure plus the laws of nature that really explains this. So you might have second thoughts about fragility, but here's another example that Ottavio also brought up this morning. Think about inertial mass. Inertial mass, as defined by Newton's second law of motion, is a dispositional property. To have a particular inertial mass is to have a disposition to accelerate in a certain way when acted upon by external forces. The object has inertial mass, and if and only if its acceleration in the closest world in which it experiences an external force F satisfies Newton's second law. That's what inertial mass is. Also, you can give it. So it's a counterfactual account of mass. It treats mass like a disposition property. But in this case, so it's dispositional in the sense in which anything is dispositional. But if it's a disposition, it's a baseless disposition. Mass is a fundamental property. There is no other property in virtue of the possession of which something has inertial mass. Also, here, if you wanted, you could postulate your way out of it, say, oh, these other properties, and there's new laws of nature that link these other properties and generate inertial mass, just as its crystalline structure generates fragility. You can also have that idea, but it would be a ridiculous view, it would be metaphysically extravagant, and it seems much more plausible to read these accounts the way the infinitesimal action view wants to read the definition of velocity. So, yeah, reading the definition of mass forward to say that having mass m in the actual world is about what happens in other possible worlds. That seems to be plausible. Better read it backwards. Having mass m in the actual world imposes a constraint on what happens in other worlds. Look, it can't be that an object has an inertial mass in the actual world, and there's no possible world in which it accelerates in accordance with Newton's second law. Just as it can't be that an object is actually fragile, and there's no possible world in which it breaks. Now, also here we've got this logical constraint. There's a kind of metaphysical cloud, modal properties in a obvious sense. It's got built into the property. So the infinitesimal action view is like the temporal counterpart of that. Now, depending on what you think about this position, it either makes it better or makes it worse. So, main argument in favor of the infinitesimal action view, it's a metaphysically cheap way of respecting what a best scientific theorists tell us about the causal role of velocity. That's the argument in favor. So if I have a causal role objection against the process view, But process theorists might want to launch their own causal role objection against the infinitesimal action. Here it comes. What velocity an object has depends on our choice of coordinate system. Yeah, whether an object moves at all and what its velocity is, kind of depends on our reference frame, what we hold as fixed. But here's a clever idea. What's real can't depend on our choice of coordinates. What's real out there in the world ought not depend on how we choose to describe it. Whether we got ourselves at rest, whether we got the surface of the earth at rest, whether we got the sun at rest, it shouldn't make any difference to what's real. But velocities depend on what's real. Locations don't, right? So you might think that that speaks against thinking of velocities as real causally active quantities. The problem with that is that it turns out that a lot of things depend on the coordinate system. That's bad news. Think back about the example of the charge in a magnetic field. And imagine we're in a coordinate system where, so we have a description. Now we move to a coordinate system in which the charge is at rest initially. So in the rest frame of the charge, so V is 0. All right, V is 0. So you might think in that case, in that coordinate system, then the charge ought not to feel any force, right? But then what would explain that even in that coordinate system, the charge moves on this weird spiral? Big mystery. Well, the solution to it turns out is that, well, in that other coordinate system, we get an electric field. That is, if we switch coordinate system, here in this coordinate system, we only have a magnetic field, then we switch to a moving coordinate system that moves relative to the one we have here. All of a sudden, there's an electric field. Electric field that in that coordinate system explains the deviation of the particle. So the value of the electric and the magnetic field depends on the coordinate system. This is just velocity. There are also other things that everybody thinks is causally relevant, such as field strength, depend on the coordinate systems. Now, again, this is what then led to the theory of relativity, precisely these puzzling things. However, what are we going to do with this? Dooley thinks that this is an argument in favor of spatial substantivalism, yeah, which gives you real velocities and gives you like the truth of all this coordinate dependent stuff. Better solution, in my view, is coordinate-free physics, which is a view we have this kind of unified thing, the electrodynamic field, and what we do, we identify physical possibilities with equivalence classes of descriptions under coordinate systems. So the way of doing physics without ever talking about coordinates, coordinate-free physics. And in that sense, we can have the electromagnetic field in that sense clearly is a real feature, and it's real but kind of coordinate dependent if we were to spell it out in a coordinate system. And so in this kind of setup, velocity is as real and as coordinate dependent as all this other stuff, which is good enough for me. There's clearly something puzzling here, but it's a puzzle for everybody. Okay, what would Hume say? Let me distinguish three different readings of Hume. First, there's the historical Hume. The historical Hume thought that Zeno's paradoxes show that time is discrete. In a discrete time, there are no derivatives and there are no instantaneous velocities. Problem does not arise. There's another reading of Hume, which Hume claims that there are no necessary connections between the states of the world at two different times. At a finite distance from each other. The infinitesimal action view respects that. What the infinitesimal action view does conflict with is what David Lewis calls the recombination principle. Lewis says that that's his way of spelling out what Hume's denial of necessary connections, and it turns out to be a much stronger principle. What the recombination principle says is that if you have two spacetimes, two possible worlds with a spacetime, you can cut out a piece of two spacetimes together with their contents, and then fuse them together, and you get another possible world. Now that's in response to something that Ottavio said this morning. That's how he thinks he can get a plenitude of possible worlds without having to appeal to modal notions, without having to say there are as many possible worlds as there are possibilities. He thinks he can get much of that by using this recombination principle. Well, if the infinitesimal action view is right, then the recombination principle is false. Because imagine at the end of one chunk of space-time, we have an object with a particular velocity. Well, then the trajectories at the bit that you fuse to it have to align just so to respect the infinitesimal action. Yeah, so on the infinitesimal action view, you have these kind of local constraints that prevent you from arbitrarily recombining pieces of space-time with their contents. So the infinitesimal action view denies strong Q, but not weak Q. Now, if you really wedded to the recombination principle, well, that's a cost of our view. But it doesn't have to reject the more plausible, stronger principle. Incidentally, what this means with the recombination principle. Imagine where space-time is full of moving objects. And we divide space-time into four-dimensional cubes. And if there are enough objects relative to the size of the cubes, you take space-time, divide it into four-dimensional cubes, and then kind of take them all apart and put them on a big pile. That's kind of a unique way of putting it back together. Okay, how much do I have left?
Oh, none.
Okay, none. Okay.
If you want questions, of course.
Okay, that people can ask questions about this stuff. Let me just so that the kind of brief summary to say that it's a view that has certain things that you have to swallow, but it's a similar view to a view that many people have about dispositions, and the main selling point is that it allows you to make sense of what our best scientific theories tell us about the causal role of velocity. And should emphasize that this discovery that velocity plays a causal role at all was really an astonishing discovery. I mean, velocity doesn't play any causal role in Aristotelian mechanics. I mean, you think about dreaming up a physical theory, attributing a causal role to velocity is not something that you can naturally come up with. Thank you.
Michel.
Are we going to ask questions about the other slides?
Thanks. This is a really provocative talk. And so I would like to say something on behalf of the process view, but think of it as sort of a very minimal process view, because the way that velocity is defined in terms of limits, he has all you need, which is, it's not, even though it says the velocity at a point, the limit requires that you consider all the neighborhood. So in a way, what you take into account is, well, the changes of the location of the object as it approximates that point. And it seems to me that that's all you need to actually capture the dynamical component. So it's not that if you say, well, look, it doesn't make sense to think about the velocity just right here, as though you are considering the velocity instantaneously. It's actually, it is a relational property. And that seems to me very sensible. It's not something that, in a way, I think it allows to address some of the worries you raised against it. It is a dynamic notion. In a way, interesting. I don't know what you mean by infinitesimal, right, on your account, but most notions of infinitesimal...
There was more on the next slide. I'll try to explain that.
Okay. So, but most notions of infinitesimal are dynamic as well, right? So you get the idea of getting to the original notion, for example, from the calculus, you get infinitesimally close, right? So, and the idea is, well, you approximate, right? And and that's what the notion of limit tries in some way to articulate. So I think if you consider the process view without the necessary metaphysical baggage that it has, it may not be as bad as it sounds, right? The other comment is about looking for coordinate-free for reformulations. I find somewhat odd for the following feature, right? There are certain things that are, of course, you expect them to depend on coordinates, right? How Michelle looks, well, depends from the perspective, right? So, and it will look differently if I'm looking from the top, from the bottom, and I want to capture that. And if you say, all right, here's my coordinate-free description of Michelle, right? We're going to make these equivalence classes of all these combinations of looks, and it said, have I really avoided the perspective? Because in each example of these classes, that will be a perspective. So I'm not sure if that's a mathematical trick that I don't think really addresses the word.
Okay. Let me start out with the second one for the coordinate-free physics. That's you're absolutely right, is that you can't just be coordinate-free your entire life. In order to get any sort of prediction, you have to pick a particular coordinate system. The point is rather that if you think that also kind of I think it's also a problem for Lewis, as we talked about so much. If you think that it's a restriction on what counts as a real causally relevant feature of the world, that it has become invalid under change of coordinate system, then basically the only things that are going to turn out to become real factors are these things instantiated at a point, because the location doesn't change under coordinate transformation. Well, that's a view you might have, but it turns out a view that is far too meager to account for what our best scientific theories count as causally relevant factors. Actually, look, the electromagnetic field. If it turns out your theory, your view entails that the electromagnetic field isn't real, I think I won. And so it's this feature that the magnetic field and the electric field are kind of, you can exchange one for the other by changing coordinate system. Super weird, right? It's like one of the most amazing discoveries in the history of physics. That is the case. So what the coordinate free account gives you is a way of explaining what the real features of the world is. So we start out with this extensionless. So we started with a feature of manifold. So it was in Charlotte's picture. We have this manifold, and then we put these objects on them. So in general activity would be the metric field. Is a dynamic feature. So we have the metric field, and we have the electromagnetic field, and they all depend on the coordinate system. The way the metric tensor looks, it's different from one coordinate system to the next. And these are the real features. So you're absolutely right that we still gotta have, in terms of how things look, they're gonna be different in different coordinate systems, is more an account of what's real. Now, about the first thing about the process view, about what is, and is infinitesimal about this here. What's infinitesimal about my view is that there are two ways of thinking about it. One, you think about it in the modern version of the calculus, which is that, we talk about infinitesimals, but we mean kind of arbitrarily close. It's a locality constraint. If you want to actually keep the infinitesimals, you think about about non-standard calculus. So we have all the real numbers that we had before, but on each real number, we have this halo of infinitesimals. We have the real number r, and then real number r plus dx, r plus dx, and so on. So around each number, we have this halo, it's kind of non-Archimedean account of the reals. So in that case, you get something that what's velocity is a feature of of a time point and its halo, right? But in terms of the regular, look at your process theories. The account that gave me is like, that's kind of what people say, it's an arbitrary kind of small neighborhood. David Albert has said, look, it's like really what we do is that the laws of physics are deterministic, not in the sense that we get this relation between instantaneous states, but like between like little time slices, and can be arbitrarily small. And yeah, it's a view you can have, but then you really need to be a process theorist. And it's a view Russell tried to explain it. It vastly complicates the scientific theories. And if you really want to be a process theorist, that's really
Russell added a bunch of metaphysics that it was not needed. So
not in the principle of mathematics. It's like this. It's no, that's not so much in the principle of mathematics. This is a chapter nobody ever reads, and it's like here's like a sketch about how to reformulate classical mechanics in his process theories. It's complicated.
Sure. Well, yes, thank you. Thank you for your talk. I have a remark, and a question. First, the remark is that it seems to me that the attractiveness of the process view of velocity has to do with its connection with observation, experience, sensory observation. But when we observe is always some finite velocity. We do not observe infinitesimal velocities. So that's perhaps one of the reasons, if I understood correctly. The second thing, I'm not sure I understood that the causal rule of velocity, because to me, it seems that velocity is a variation of space in time, and this seems to be an effect in physics of forces, for example, are usually taken to be causes. So if there is a causal rule of velocity, I don't see what it could be, except that it is an effect of something else, which is not a velocity and which is a cause.
Well, the answer is both. So if you think about Newton's second law, so according to Newton, forces accelerate. So like in Aristotle's objects stop moving, stop pushing them. So Aristotle's forces cause velocity. In Newton, they cause acceleration. So it's true that on the one hand is that forces determine velocity because they determine accelerations. But the remarkable thing in relativistic theories, you can also get the opposite, where the velocities determine the forces. Again, a particle is moving in a charged particle, moving in a magnetic field. The force that the field exerts on the particle depends on its velocity.
Yes,
And I think what you express is that it's completely right in that it's like, how can that possibly be? Is the velocity always an effect of the force? Yes, it is, but sometimes it's also that the forces are an effect of the velocity. And that's the astonishing discovery.
Yeah, you're right, but you can see things in this way. Is that the variation of velocity or the amount of velocity determines the value of the mass. Sorry, the value of the mass determines or contributes to the value of the velocity. Yes.
Yeah. So, but see, that way around is unproblematic. That there's something that the velocity has an effect. That's unproblematic. I mean, in average velocity is clearly an effect, right? What's remarkable is that in our theories, velocities also function as causes, and the process theory has a problem with that. It's something that only emerged with Newtonian theory. And also on the other point that you made about our observation is always it's extended with kind of discrete observation points. what we have here is a remarkable discovery that it's both it's a physical discovery, but it's also something that only emerges in a theory where both space and time form a continuum. And the continuum that vastly outstrips our observational capacity. Our observational point are always going to be at most like on the, at most as many as are rationals, but then the continuum kind of vast, it's kind of vastly larger than any of them. So you're absolutely right about the observation, but these theories that we have here go kind of enormously beyond whatever observational data points you might have. They're kind of bet one rather than finite.
Alastair, a short one?
Yeah, thank you. So really interesting stuff. I wasn't quite sure why it was that you said that you don't have to deny weak cube here. It kind of seemed to me you did. Perhaps the next slide was going to help explain that.
Well, the element is kind of the worry is like that's what you want to see. So here's one worry that I have. So I have these kind of infinitesimal constraints. Now, velocity at one time constrains its locations at infinitesimally later times. And the objection, so and it says, oh look, but it's only infinitesimally deep. That's why we have to reject the recombination principle, but not diachronic. We don't have to accept diachronic necessitation. And the worry here is that you can get diachronic necessitation relations or the infinitesimal ones by integrating.
Yeah.
Now it's like the velocity at a later time, you just kind of integrate all the accelerations, and then to get velocity, you just integrate all the intermediate velocity. So then I have 5 slides that explain why.
Could you just go back to for a second, sorry, to the previous slide. I mean, the weak Hume claim was at the necessary connection in different times.
Yeah.
And like infinitesimally different times are still different, even if I mean infinitesimally different. So
well, that's a bit where I fudged a little bit about what I explained what I mean by infinitesimal. It's only in the limit. So if you take any two, here's something that's true. If you take any 2 times, the state of the world at one time imposes no necessary constraint on the state of the world at the other time. It's so infinitesimal. No matter how close one time is to the next, kind of. So they're always like continue many time, but in between.
Okay, so I think I'm getting the idea. So it's like that there's pick any 2 times, and there's no constraints between those.
Yeah.
I was worried about the sort of quantificational thing. There is a time that it imposes a constraint on.
No, right. No, it isn't. Yeah. Yeah. Yes. Yeah. Sorry.
Thank you.